Multicollinearity in R. In this video, I'm going to show you how you can detect the problem of multicollinearity in R and how you can resolve the problem of multicollinearity in R and in SPSS. So first and foremost, I'm going to look at that of multicollinearity in R. First and foremost, what is multicollinearity? Now, that word linearity simply means something that is related to each other on a parallel line, or something that is related to each other on the same rate. Something that is related to each other on the same rate. For instance, you have two objects A and B. If they move at the same rate, if A moves at the rate of 5 meters, let's say A moves at the rate of 5 inches, B, or it also leads to B moving at the rate of 5 inches. And A moves again at the rate of 5 inches, B moves at the same 5 inches. So these things are linearly related. Now they move at the same rate. So now when I say multicollinearity, that means that something that is multi, it occurs more than once, it occurs multiple times. So multicollinearity is a problem in our is a problem, but not really a problem in our OLS estimate, that is in our regression analysis in our output. Because once you have the problem of multicollinearity in your data set, in your estimate or in your data set, you are bound to, because it's bound to give you a bogus, or a wrong estimate of your parameter, or rather, it's bound to give you a wrong. It's bound to give you a wrong estimate of the variance of your data set, not the parameter but rather the data set. So multicollinearity. Now, one of the assumptions of the classical linear regression model is that the independent variable should not be exactly correlated with each other, just as I've mentioned. You will have various variables like x1, x2, x3. If x1 moves at the rate of 5 times, x2 also moves at the rate of 5 times. X1 moves at the rate of 5 times, x2 moves at the rate of 5 times. This is exactly correlated with each other. But if x1 moves at the rate of 5 times, x2 moves at the rate of 3 times, x1 moves again at the rate of 5 times, x2 moves at the rate of, let's say, 3 times or 2 times. Now, these are not exactly multicollinearity. Now, if x1 moves at the rate of 5 times again, x2 moves at the rate of 1 time, x1 moves at the rate of 5 times, x2 moves at the rate of 4 times. Now, you can see that is not exactly multicollinearity. So therefore, now one of the assumptions of classical linear regression model is that your data set the independent variable should not be exactly related with each other. That is, they should be independent of each other. That's your x variables should be independent of each other. They should be exactly related to each other. Now, the moment your independent variable, your x variables are exactly related to each other, that violates one of the assumptions of the classical linear regression model, and this leads to the problem of what we call multicollinearity. And once you have this problem of multicollinearity, then it affects the estimates of your model. That is, your estimates of your model is being affected, but nevertheless, your estimates of your model is still blue. Remember, we have different methods of regression analysis. OLS is just one method of regression analysis. The ordinary least square method is one, and is the best because it produces the blue estimate. In other words, it produces the best linear unbiased estimator. So once your data set violates the assumption of exact collinearity, the assumption of independency among your independent independent variable, that they are not independently related, that is they influences each other, then that assumption of independency of your x variable is violated, and that leads to the problem of multicollinearity. And the problem of multicollinearity will now lead to it will lead to an increase in the variance of your parameter estimate. Now, It leads to the increase in the variance of your parameter estimate, but your parameter estimate are still blue. In other words, your parameter estimate, your output result is still best, is still linear, and is still unbiased. It can be useful, but nevertheless, the mean of your parameter estimate, the mean value of your parameter estimate, the mean value actually will deviate from your parameter estimate will deviate from its mean value at a very large extent. That is what will be shown by the problem of multicollinearity. The variance will be so high, then that would be that it will indicate that your parameter estimate deviates from its mean value at a very large rate, and this will also affect the confidence interval, which will lead to the acceptance of the HO, the false null hypothesis, when it should be rejected. As a result of that will affect policy making for policy purpose, and also it will affect making decision at the end of the day based on the results of your data set. So, however, multicollinearity is not a problem of the kind or the nature of multicollinearity, whether it's a perfect multicollinearity or is an imperfect multicollinearity. But multicollinearity is a problem of degree. To what extent is your model affected by this problem of multicollinearity? Now, without wasting much time, let's dive into the app and let's see. Now, first and foremost, my dataset is located in the Excel spreadsheet. I want to install my dataset. I want to import my dataset into my app. So I'm going to install this. Because my dataset is located in my Excel spreadsheet. So I'm going to use install. Okay, install the packages. This is what I'm going to use. Now I already have this installed in my app, so I don't have to install it all over again. But if you don't have it installed, you have to install that. Then I'm going to activate this. Okay, I'm going to activate it. So once you finish running this line of code, you run this other line of code. Now I already have that installed here in my app. This is already installed in my app, as you can see. I already have this installed in app, so I can just need to only run this particular line of code, and that activates it. Now the next I'm going to install is this. What I'm going to install next is the other package. Now I need the other package because I want to use the pipe function. Because of the pipe function, that's why I want to install this package. So you run this line of code. Now, if I already have this installed in my app, so once you run the first line of code, you run this other line of code to get it installed. Now I already have that installed in my app, so I could either run this line of code to activate it, or I simply click on this checkbox that activates that particular package. Now I want to import the dataset into app, so I can start using, let me use this name, cat64 underscore. Now I want to import my dataset into app. My dataset is located, this is my dataset, and if I'm working on the same directory, except you're working on a different directory, and this is my dataset. My dataset is located in this particular folder. Yeah, this particular folder. This is where my dataset is located. So I could simply type set working directory. That if you're not working on the same directory, you could set that as your set working directory C/ user / vim / documents, okay, /r programming. But if you are working on the same directory, I don't think we need to do that. Let me see, get working directory. Now that gives me that once we run this particular line of code, that gives us the working directory. Now you can see we're going to see user vim dot. So if we are on the same working directory, okay, then we can use this now, and we use the read underscore. Now I can use this, or I can use this particular function to import my dataset into R. And the name of my dataset is car sales 4. So car underscore the sales, and I for then I have to use the extension dot xl x x x l x l s x. Now, okay, if we are really working on the same directory and run this particular line of code, now it's telling us that this path does not exist. Now that is what we have been told, that this path does not exist. So we'll run this line of code. Though when we run this, we've gotten that we are working on the same directory as users, as vim, and as docs. And okay, let's still run this particular line of code. Let's set the working directory to that. Now setting the working directory, let's still run this line of code. Is fine. Now we run the line, but now we can see our dataset. Here is our dataset in R. So this is our dataset now. This is the dataset about the sales of vehicles, and we want to see if the sales of vehicles is affected by the types of vehicle, the engine size of the vehicle, and the fuel efficiency of the vehicle. If these three variables influences the sales of the vehicle. Also, we are going to check all this other, the wheelbase, the width of the vehicle, the length, the cubic weight, and the fuel capacity. If all this also have the horsepower, if all this also affects the sales of vehicle. But for now, we just stick only to these three variables. Now, since my data set I have more than one variable in my data set, I only need those three variables, and 4 variables rather. These are the 4 variables that I'm interested in. So first and foremost, I'm going to use the pipe function to select these variables of interest. I'm going to use a pipe function to select the variable of interest. That was the reason I install this package, so I can use the pipe function. So I'm going to use the pipe function to import this variable of interest. Okay, now I'm going to use a select. That's a select function. Now these are just the 3 variables of interest, that are the 4 variables of interest that I needed. I do this. Okay, fine. Then we can now run these 4 variables of interest. What is it? Let us see. Could not find the function select. Okay, could not find the function select. Now we have to get the function select to be selected. Okay, the function select is in the what package? Can we really see the function select? We have to check the package where we can get the function select, that the select is part of one of a function in R. So we have to look at the function select. We have to get the package where the function select is part of a function in R. So that is what we are going to do. So that's what we're just going to check how we can select what package the select belongs in R. So once we check the package, the select functions belong in R. We just check the package select function belongs in R. Not that. Okay, now. So because of that, then we have to install okay, so we are going to install another package known as the dplyr function package. That is okay. Now that so the select function is part of the dplyr package. So the select function is part of the dplyr package. So we are going to select that. So you're going to run that and run this other line of code. Now I already have the D package here. So all I need to do is to activate that, and then let's run this again. And let's see. Now I've run that. Now that's done. So that now I've selected that. Now I have those three variables selected. Now the first way of testing multicollinearity in your dataset is to run a correlation analysis of your dataset. Now let me save this. I want to save it in this object. Okay, let me just give it another name. Let me call this underscore collinearity, and let me copy this and then save it here. Okay, fine. So the first way of checking if there is multicollinearity in your dataset, the test for multicollinearity. Test for multicollinearity. Now, the first way of testing for multicollinearity in your dataset is to run the correlation analysis. Now, when I run the correlation analysis of this particular dataset, that will tell if there is multicollinearity in my dataset. Now you can see that gives me the correlation matrix. Now you can see that I'm interested in the independent variables. These are my independent variables: the type of vehicles, the engine size of the vehicles, and the fuel efficiency. If these three affect the sales of the vehicle. Now, so I'm going to see the type of the vehicles on the engine size of the vehicle. Now you can see that is approximately 0.2, and then type of vehicle on the fuel efficiency is a negative approximately 0.5. Up to 0.5 is not up to 0.9. The rule of thumb is that once your correlation analysis between two variables is up to 0.9 or up to 0.8, then there might be a problem of multicollinearity. Those two variables might be linearly correlated with each other. So now my engine size and fuel efficiency, the correlation between these independent variables, the three independent variables, the relationship between these three independent variables is not up to 0.8. That determines that my data set, my independent variable, there is no problem of multicollinearity in my data set. But nevertheless, further diagnosis is still eminent, is still needed. So if we want to carry out the further diagnosis for this, we can decide to run the LM test. Now the running the LM test now will help you to running the LM test will help you to run the regression analysis and test. Okay, now running this will help you to run the regression analysis of the dataset now. So we've seen that the correlation here is not up to 0.8, so that means there is no problem of multicollinearity in our dataset. So running this line of code, now I've already have this packaged installed. So I don't need this. So all I need to do is to just I have it to install twice. Okay. Then that activates the package. Now, after we've activated this package, then we want to run the regression analysis. Now, running this regression analysis, LN, we could call a regression model. Then we use that function. Now we need a formula and the data. So let's say formula equals to equals to then the data set, the data. Okay, what is the name of our data? This is the name of I finally gave my data. Now the formula is equal to my dependent variable is sales. The sales is a dependent variable. Then the other variables of interest are this. The other variables of interest and this three. Okay. So now I'm going to use the type. I want to see if the type of vehicle influences the sales of the vehicle. Okay, if everything is done perfectly, I will run it. We won't run into any problem. Okay, fine. That gives us that makes okay, fine. Now this gives me the estimate of my model. Now you can see the type, you can see the engine size, and you can see the estimate for the fuel efficiency. Now, if we want to check for the if we want to check for if we want to check for the coefficient, we want to check for the t-test, the standard error, and to check for the significance of this. Let's see the summary statistics. Now I think error. I'm able to find an inherent method for function summing for the city mixture. Okay, X. Now I jump. Now let's see if we can if this t function will give us this the time degress. I want to see the summing function. Let's see how we can work with that the summing function. Let's see if we can work with that. Let's see how we can work with that. Okay. Let's see these two functions if then it will be of help. I think yes, we are not getting that. Let's try installing. type the summary, we mistakenly picked the wrong summary, or we mistakenly picked the wrong summary. Now this is not the right, this was the one we mistakenly picked. Now there is another summary down here. There's another summary here. This is the summary we also have picked. Then we use the RM. The moment we run this line of code, that gives us the estimate of parameters. So this gives the estimate of our parameters. Now we can see the standard error, we can see the T value, we can see that only the types of vehicle are actually significant, that actually influences the sale. Only the types of vehicle actually influences the sales of only the types of vehicle actually influences the sales of vehicle. Now the fuel efficiency and engine size does not have influence on the sales of vehicle. Now we can see based on this that though out of our three parameters, out of our three variables, only one variable is significant. And we look at the R square. The R square is not I. So that suggests that there is no problem of multicollinearity in our data sets. Now, this further confirms that there's no problem of multicollinearity in our data set. One of the ways to detect if there is a problem of multicollinearity in your data set is if you have a very high R square of like 80-something%, R square of about 80-something%, and very few of your variables are significant. Now, in a particular, then that indicates that, or it shows a sign of multicollinearity in the data set, or it shows a sign of multicollinearity in the data set which you have to look into. But based on this result, there is no multicollinearity in our data set. It further confirms the result we got using the correlation matrix here. The correlation matrix also confirms that. Then we can now check for multicollinearity using the performance test. So the performance package. So once we've installed this particular package, I've already installed this package in R. But when you install this particular package in R, you'll be able to check for multicollinearity, autocorrelation, heterozygosity, and the rest of them. So I already have this package installed in my app, the performance. So let me just activate that. Now, so once I've installed, you've gotten that installed, you run that particular line of code. I cannot check for multicollinearity by using check for multicollinearity. Now I can also check for autocorrelation, but I'm looking at multicollinearity. So I click on that. But when I check for multicollinearity, I'll now copy this and paste it here, and I run this line of code. Now running this line of code will give me the variance inflation factors and the tolerance value. Now based on the variance inflation factor, our variance inflation factor is less than 2. That tells us that there is no multicollinearity in our data set. Now, some textbooks say the rule of thumb is up to 10. Once you have a variance inflation factor from 10 and above, that indicates that there is a problem of multicollinearity in your data set. But if it's less than 10, why some say once it's less than, so I'm looking at using the rule of thumb of 2. Once your variance inflation factor is less than 2, that means there is no problem of multicollinearity in your data set. So based on this result, our model has no problem of multicollinearity in our data set. Our data set is free for the problem of multicollinearity. And you can see this is telling a low correlation. So the correlation is not high to indicate a problem of multicollinearity. And also we can look at the tolerance value. The tolerance value, the closer it is to 0, the more likely for the problem of multicollinearity to be in the data set. And you can see our tolerance value is closer to 1, 0.78, while the list is 0.62, is more closer to 1 than 0. That further strengthens our diagnosis that there is no multicollinearity in our data set. So since there's no multicollinearity in our data set. The tolerance value is gotten by dividing the inflation factor by 1 all over the variance inflation factor. Now, once you hit this, that gives you the tolerance value. So based on all these results, that tells you that there is no problem of multicollinearity in our data set. We might want to plot this to further confirm by visualizing that to see if there is a problem of multicollinearity in our data set. Now, based on that, you can see that these are green. So to tell you that our model has no problem of multicollinearity, that there is no problem of multicollinearity in our model. Now you can see that the multicollinearity is green. Now if there is a multicollinearity in our model, it would have showed red. It would have indicated with the red, that which is telling you an alert. Another way of checking for multicollinearity is to use the multicollinearity and then RM. So that's another way of checking multicollinearity in your model. So the moment you run this line up, it gives you the same thing. So you can also plot that. Now that is multicollinearity in R. So, but you can see our data set. But if we want to use, why we imported this data set now, we have a lot of you can see we have a lot of columns. If we want to use those other columns, such as the engine size, horsepower, the wheel bar, the wheel base, the width of the car, the length of the car, and up to the fuel capacity of the car and you want to include these other variables. Now you can see we have too many variables. So you want to see if the sales of car is influenced by all those variables I just mentioned. What we are going to do now, we are going to still select, and we are going to, because our model has all this, I don't want to include all this, the Z value of the engines of each of these variables. Now I want to exclude those variables out from our data set. Then we can use the select function. I've done that there. We can simply copy this. Because there was too much, and okay, we come to the side and we paste it there. Now you can see we can select that. Now you can see how lengthy it is. So we can use the select function. We select this. Once you run that line of code, that selects pick all those variables. Now you can see all those variables. Now these are the only variables that I need for this. Alternatively, if you can see I make use of minus for each of this. Now if you don't want to add a minus sign for each of this, the minus sign means you don't want this particular column or variable to be included in the model. So that's the manufacturer, the model, the reseller, the price. That is all this column: model, manufacturer, model, reseller, and so on and so forth. You don't want to just put a minus sign for each of them, or alternatively, you put a minus sign and you put a C and the bracket, then you put everything inside the bracket. So either you run this or you run this. Then I've done that, then I save this just the way we did this, what I did here. After running this, I save it in this particular object. So I used the same thing. After running that, I save it in this particular object. Now we save that in this particular object. Then we want, now we can't run the correlation metrics for this. Running the correlation metrics for this, it will be too lengthy because we have too many of the variables. Now we have too many of the variables, so to run the correlation metrics for that will be too lengthy. So running correlation metrics for this, it will be too much. So now some of the variables are not even numerical in nature. X must be numerical. That means some of our variables are not numerical in nature. We have to even change it. So besides the fact that it will be too lengthy, some of the variables are not numerical in nature. So let's just leave that. Now, if we want to run the LM result for those variables, now we can copy this orders and then we'll decide to run the regression analysis for all those variables. Now, since those variables are too lengthy, Another method we can use, if you don't want to list all these variables, these three variables we just listed, we can just use a dot, that is a full stop, that's a period, and run this. When we run that, that will also gives us that also do the magic. It also gives us the outputs. Now you can see. So that does the magic as well. So now you can see that. But in this particular case now, I want to replace that with this. Rm is equals to, I want to replace this with that. Okay. So instead of that, let's get it with this. Okay. Now we'll be running for all those other variables. Now that runs it for all the other variables. Okay. Now you can see that now these are for the lengthy variables. You can see the lengthy variables. Now you can see for all those the variables. Now you can see that now you can see the type, the horsepower. Why? Because this data set, you can see now these data sets, we are finding it difficult to determine the value of each of the independent variable in these data sets, like the wheelbase. We are finding it difficult to determine for each of those data sets. We are finding it difficult to determine the estimate for the horsepower, the wheelbase, the width, the length. Why? Because of the problem of multicollinearity. One of the problem of multicollinearity is that once there's multicollinearity in your data set, you have the problem of indeterminacy, difficulty to determine the value of your independent variables. So that is what we are facing here. And we now look at the R square. The R square will be perfect. So the R square, we have a perfect R square. When you look at the R square will be a perfect R square, like 100%. Now you can see the R square is 1. So it's telling you that there is problem of multicollinearity in this data set that is more than 1. We are having issue with it, problem to determine the estimate of the data set, and so on and so forth. So one of the ways to resolve this is to drop some of these variables. You can just is to drop some of these variables. That is one of the ways to do that. So it's to drop one of these variables. The moment you run this now that I did with that, it is not even going. So it's to drop some of the variables the way we did here, that we only selected few of these variables. You can see I had to only select out of these variables. I dropped those variables. So that is what we are going to do. So what we need to do is just to drop some of the variables, and then once dropping some of the variables, that will solve the problem of multicollinearity in your model. So that will resolve the problem of multicollinearity in your model. You can see I've dropped the variables, and I only used just only the selected variable, and that will resolve the problem of multicollinearity in your data set. Fine. That resolve the problem of multicollinearity in your data set. So that is how to detect multicollinearity in R. And let's see how we can quickly do that in SPSS. SPSS, we're not going to waste much time with that. You go to analysis and you go to regression. We are interested in the linear regression. Now, once you get to linear regression, first and foremost, I said the first way to detect is to run a correlation analysis based on your variables. Now, I just pick my variables. Those are my variables. I run that. Now you can see the correlation analysis that's on all these variables in R. When I look at the engine size and the fuel efficiency, you can see the correlation is high. The correlation is high. Engine size and horsepower, correlation is high. The weight correlation is high with the length of the car. Engine size of the car and the length of the car, do you see that is high? And you can see the engine size and the cubic weight and fuel capacity that are all high. This will tell you that there might be problem of multicollinearity in this data set. So you are expected to diagnose further. So that is what is just telling us that there might be problem because of the high correlation among the independent variables. So now I can now decide to run the regression on all these variables, and then let me add those variables, those ones that I've not added to the data set. Now, okay, this for collinearity. Okay, let me do everything at once and run this. Okay, fine. I'll run this variable. Now let's look at our results. Now you can see based on our standardized coefficient results, you can see that based on that result, you can see based on this result, the significant value, you can see only how many variables is significant. Engine size is significant at 5%. The horsepower is significant at 10. Wheel base is significant at 10. While cubic weight is significant at 1%. Okay, now that's it. 4 variables are significant out of how many? 1, 2, 3, 4, 5, 6, 1, 2, 3, 4, 5, 6, 7, 8, 9. Out of 9 variables, only 4 of the variables are significant. So that is telling that 1, 2, 3, 4. Now only 4 variables are significant. That tells you that there might be problem of multicollinearity in our data set. Now based on the correlation analysis we've done, now looking at the estimate of our model, few of the model is significant, while the rest 5 is not significant. There might be, not necessarily, because 4 out of 5 is still okay, but nevertheless, let's diagnose for that. Let's look at the tolerance value. Now the tolerance value is a little bit closer to 0, that's 0.2, 0.3, 0.4. The tolerance value is not up to 0.5. Now we look at the variance inflation factor. The variance inflation factors are more than 2. That should tell you that indicate that there is a problem of multicollinearity in our data set. Now let's look at the collinearity and let's diagnose it. Now this is the multicollinearity output. So let's diagnose that. Now looking at the engine values, the engine values are more closer to 0. The more closer to 0 the engine value is, the more likely there is the problem of multicollinearity in the model. So you can see the engine value closer to 0. This is our multicollinearity result. Now it's saying that this output, this model has the problem of multicollinearity. So we have to drop some of this model. Now when you want to drop some of this model, you look at the model that are highly correlated to drop. For instance, we have the engine size, fuel efficiency, they are high. We have engine size and price, engine size and horsepower. We can decide to drop horsepower off the model, and we can also decide to drop the cubic weight of the model, the fuel capacity of the model. Some of these that have a high correlation, though the correlation is not up to 0.8. That is that the problem of correlation, multicollinearity in this particular model is not that too serious, because when you look at the variance inflation factors and the tolerance value, also the estimate of our result, 4 is significant out of 9. So it's telling that it's not too severe, but the collinearity diagnosis, the multicollinearity result is telling us that there is a serious problem of multicollinearity in this model based on the engine value as we look at the multicollinearity result. So we have to drop most of this variable. So that means we have to drop most of this variable and run the regression analysis all over again. So dropping most of this variable now, and let's drop that. So from this point to this point. Let's drop all that and leave just only the three variables we had before and click on OK. The moment we do that, let's check our results all over again. Now, checking our results all over again, we can see now checking our results, only the variable type is significant, similar to what we got using the R. And we can see the variance inflation factors are still similar to what we got before. The tolerance value is still significant to what we got before. But now, when we now look at the engine values, the engine values here, you can see the engine values is 0.6. Just only 1, 2 is closer to 0. So this is how to detect the problem of multicollinearity in R and SPSS and how to resolve it. How to resolve it, drop some of the variables that is causing the problem of multicollinearity in your model, or increase the size of your sample size of your model. But in this particular case, I've dropped some of the variable causing problem in the model. If you love this video, kindly give it a thumb up. Give it a thumb up. Also, remember to subscribe to our social media channel, our Instagram channel, our Facebook channel, and our TikTok channel. Thank you very much for watching till next time.